So I'll be indeed speaking about the modeling of deep network for image processing, trying to introduce some of the important questions and also present the work more specifically of collaborators and PhD students that I will detail on the way. So deep convolutional network, I suppose all of you know the structure. I suppose also most of you are now using it if you're doing image processing. Basically, you have these processing of images which are constructed by alternating convolutions with non-linearities, which nowadays are mostly ReLU, so just picking the positive part of a number modulo a bias, and then iterating that kind of transformation where the convolutions are done along the many channels, and each time you perform your convolution, usually on a small support, subsampling, which gives the next layer, and again applying the nonlinearity and so on, until the last layer where you essentially make a linear combination of the coefficient to get the output. So the output for what? The output for doing predictions, classification of images, dogs, cats, whatever structures in, for example, medical imaging, but it can also be for segmentation of images, even compression, suppression of noise, solving inverse problems. Basically, essentially, all areas of image processing have been progressively invaded by these deep networks, to the point that sometimes we are wondering when you go in an image processing conference whether it's not just an applied deep network conference. So you get beautiful ideas, amazing results, new architecture constantly, but we're still not really understanding why these architectures are working so well. And what is amazing is that the same kind of architecture works for images, but also for natural language, also for regressing quantities in physics, like in quantum chemistry and so on. So there seems to be some principles which are much broader even than the domain of images. So the question is, what kind of mathematical model one can develop to begin to try to understand that kind of structures? Now, when you think of images, if you are thinking of mathematical models, let's say about 20 years ago, we were thinking about edges, corners, structures, geometry, curves, and so on. And it's totally different approaches that are coming in to try to understand the nature of images. And that's what I would like to detail a little bit. So first, when you look at a problem like trying to predict a quantity, let's say classify an image, so estimate this parameter y here, that would be, let's say, the class label from the image that has a lot of pixels, typically millions, you have two ways you can look at the problem. If you are on the Cartesian side, which would be my own tendency given that I'm French and I've been mostly working on the deterministic side of mathematics, well, you think at the problem the following way. You have some training data, so you have some values of your data for which you know the value of y, and this training data is spread over the domain. And now you want to compute a new value y for a new value x. So it's about interpolating the function. So that can be thought in terms of function approximation, trying to get the best, in some sense, interpolation. The only problem is that you are in high dimension. So one naive question is it more difficult to estimate this quantity y when the dimension increases? If you think in deterministic term, you would think, yeah, it gets much more difficult, because when the dimension increases, the volume of the domain where x is going to live is getting much larger, and you have what is called this curse of dimensionality. And in order to avoid this curse of dimensionality, because you are not going, the number of samples you would need to cover your domain would grow exponentially with the dimension. In order to avoid that, because you have a limited number of samples, you'll need to make some hypothesis of very strong regularity on the function f, and then think what kind of functional spaces can explain the kind of results that these networks are obtaining. Now, there is a totally different way to think about exactly the same problem, which would be the bias, or which is view of the world, which is a probabilistic view, which would consist in saying the following thing. Okay, we're going to define a probability distribution, and we are going to try to compute the probability that the class is y, given that the observation is x. Now, a bias classifier will try to find the y which maximizes this probability. Now, if you apply the Bayes theorem, you can write this probability as the probability of x given y multiplied by the probability of y divided by the probability of x. If you want to maximize over y, you don't care about the probability of x. So it's essentially about maximizing that. What is this? This is the probability of finding the x given y. So how many x do you have given y? It's the set of points which are on this line. So it is this leveled set of the function, the set of all possible x where f is equal to y. When you change y, you have a different set. So when you think in probability terms, you begin to look at where the data is concentrating, given that you know the value of the class. And when D is getting large, you observe a concentration phenomena, which is getting cleaner and cleaner because of the law of large number. So in some sense, when D increases, you have this intuitive observation that you have more data. And if you let your data vote, you are going to be more and more sure about your decision Y. Totally the opposite point of view. But the mathematics also are very different, because you are not anymore going to think as x being a dummy variable that lives on an interval, say 0, 1, but as a variable that is going to concentrate in some part of the spaces. And what you'll need to define is where are they concentrating. In other words, you need to define probability distribution models. Now, the reason why this point of view seems to be the right one, first of all, that's the point of view that usually engineers are using to try to define their cost function. But also, if you now look within these deep networks, if you begin to look at the evolution of your X across the layer, people have observed, and in particular, there is a beautiful work by Papian, Han, and Donohoe, which shows that as you progress in the network, the data corresponding to one particular class begins to concentrate in a particular region of the space. And as you go deeper in the network, you see that the different classes have a tendency to get separated and more concentrated, so that in the last layer, it's really simple to do the discrimination. You just have to find the direction of the different blobs where your different classes have been concentrated. So that means that one image of a class, let's say yellow, is going to end up in this very concentrated region of the space. So the question is, how come you have that kind of concentration and separation phenomena? Why is depth so important? Why not a shallow network? What is the role of these nonlinearities that are being applied? And of course, you have these operators that you learn. Do you really need to learn them, or can you guess them from some priors, or what is absolutely needed to learn? So these are the typical kind of question that you can wonder when looking at such architectures. Now, other type of problems, which are in fact very important in image processing, is not just to predict let's say some quantities, but also just to model the data. This is very important for compression, for inverse problem, where you want to build a model which will give you some prior in order to solve an inverse problem, for example, which is ill-defined, or in order to separate the image from the norms. Now, what has been observed is that these networks are also very efficient to build models. And that's an example of a work by Matthias Bedge and their teams, where the network has been trained on a standard database, ImageNet. Then what they do is for each layer, they just compute the correlation between two images of the given layer. So they get a certain number of statistics that they compute from a single image. And then they reconstruct new images which have exactly the same correlations and with a gradient descent algorithm. And the surprise is that if you give a single image of turbulence, you can reconstruct many images which looks like turbulences. These are different examples. Bubbles looks like bubbles and much more complicated texture. Why am I picking the example of turbulence? Because since the 1940 and the first paper of Kolmogorov, physicists have been working for now about 80 years without being able to come out with good probabilistic model of turbulence. And suddenly you see these networks which seems to be able to build such models. What mathematical interpretation, again, of that kind of superb results. So the talk, I'm going to look at the two types of problems. I'm first going to begin with unsupervised learning and trying to show how you can build complex models of probability distribution. So that will lead us to information theory, statistical physics, and multiscale representation, wavelets, because you've seen how these networks seems to look at the data progressively on coarser and coarser grid. The strategy here will be to begin with simple problem and move progressively to more complex problem without learning as much as we can. And then we'll move to supervised classification problems, such as, for example, classification of images in ImageNet. And then we'll see why learning is so important and what kind of learning, what kind of questions comes from that. So this notion of concentration, let me begin with that. We're back now to Shannon theory of information and this spectacular observation of Shannon, which is that if you have n random variables, so a signal of dimension n, but I'm going here to suppose that the coordinates are all independent, then the probability distribution of this, let's say, image is just the product of the probability distribution of each pixel, let's say, of the image. Now, what is the law of large numbers saying? If I'm taking the log of the probability of P of x, why am I taking the log? Because now this product is going to be a sum. But if each pixel is independent, these are independent random variables. So you are making the average of independent random variable, and the law of large numbers tells you this is going to compute to the expected value, going to converge to the expected value. And the expected value of the log, it's called the entropy. So you have this phenomena that if you take the log of the probability of a very high dimensional data, it has a tendency, if you have some independence, to converge to the entropy. This is not just true for independent random variable, but also for ergodic stationary processes, which have correlations, but which are big enough so that the law of large number can apply, and it converges to the entropy. So what's the relation with concentration? What it means? It means that with a very high probability, if you take any realization, any example samples of X in Rn, then the log probability is going to be close to H. In other words, the difference with the entropy is going to be smaller than epsilon for n large enough. That means it's going to belong to a very particular set, which is called a typical set. And the size of this typical set is precisely given by the entropy. So that shows that the data doesn't live everywhere, but in a subset. And of course, for coding, you'll just have to code the coefficient in this subset. That's a phenomenon of concentration. So now you want to build models. How can you do it? So that's the idea introduced by James in the 60s. And coming from statistical physics is to say, well, what you can do is just measure averages of some nonlinear function of X, an expected value. And one way to build a model is to try to define a probability distribution which has the same average as the true distribution that you can compute empirically from examples of your data, and say that you don't know anything else. In other words, maximize the entropy of the model. And one theorem that was proved by Boltzmann and Gibbs is that if you impose this condition, in other words, impose that you have the same average value than the true probability distribution, but a maximum entropy, then you are building a model which is an exponential of the linear combination of your moment functions. So this is called a Gibbs distribution. In other words, you can have very nice exponential models just by imposing moments, and the parameters of the linear combinations, which specify the probability distributions, are the Gibbs parameters. The central question is, of course, what should be these famous moments that are going to characterize the probability distribution? So the idea is that the log probability is going to be approximated by a simple linear combination that was given by the theorem of the function of the features, if you wish, of the data. So how to choose the feature? Well, if the log of P is written as a small linear combination, that means that the property of P of X should be found within these phi of X. For example, if the process is stationary, then P of X is going to be invariant by translation. You should choose your phi of X as being invariant to translation. If the probability distribution is invariant by rotation, you should choose your features to be invariant to rotations or deformations and so on. Okay, what is the simplest model? The simplest model are second order moments. You just correlate X with X translated. This is a bilinear form. So the model is going to be an exponential of a bilinear form, and you get a Gaussian distribution. Now let's look what it gives for the example of turbulence. Here are two examples of turbulence. These are the models that are obtained as having exactly the same second order moments. That was the model of Kolmogorov. And you can see that they are very far from the true model. So the question is how to do better. The first reaction was to think, well, let's try to build high order network, high order moments, but it doesn't work because you have too many of them and it creates high variance estimators. Deep network generation looks much better. Why is that? So then people in physics obviously have developed much more sophisticated models by imposing not just second order moments, but also some information about the marginal, the distribution of the field at different positions, and that's called scalar potentials. Now, what did they observe? If you have a simple model, that's a model that was used to characterize the magnetism of the ferromagnetism of iron. So you have the spins that can be positive or negative. If the temperature is very high, the spin are going to be disordered. And what they observe is that if they build a simple model like that, if the temperature reaches a certain level, which is called a critical temperature, suddenly the phenomena change completely, exactly as in phase transitions when you go, let's say, from water to gas. So what that shows is that when you change these parameters, you have something very unstable that can happen. And that makes it very hard to estimate these models. Now, again, ideas came from physics to try to solve that kind of questions. In particular, in the 70s, there was this idea of renormalization group. The idea is the following. You are going to have a parametrization which is very unstable. However, what you can do is look at your distribution at different scale. So you just average and coarsen up your images. And if you look at the evolution of the probabilistic distribution at different scale, you observe that this evolution is in fact very regular. So much that if you are exactly at the phase transition point, the probability distribution are going to be constant. In other words, you have no instability. So how can you use that kind of observation? Pick an image. you can look at the coarser scale version of this image, and you can extract the details with a bunch of filters, which are the so-called wavelets, which are oriented. These are the high frequency component of the image, which are sufficient to recover the original image from the low frequency. I will call them delta X as like the difference as opposed to the coarse images here. And then you take the coarse, you can subsplit it again to get the details, which are again the wavelet coefficient at the next scale, and so on. So what is that going to bring? And that's the work of Thierry Marchand, Misaki Ozawa, and Giulio Biroli in this collaboration. If you want to build a model of an image, you want to build a probability distribution. But the x0 is equivalent to having the low frequency and the wavelet coefficient. So it's the probability distribution of the joint distribution of the low frequency and the high frequency. You can write that as the probability distribution of the high frequency given the low frequency. So you make a hypothesis of the high given the low. Let's continue. You take the probability distribution of the low frequency, you split it as being the probability distribution of the wavelet coefficient given the low frequency, and so on. What do you obtain? You obtain a decomposition of your probability distribution in terms of conditional probability distribution. Now, why is our renormalization group results telling us, so theory, is that it is unstable to compute the probability distribution of the low frequency of these images, but these ones, in other words, the interference between the high and the low frequency can be estimated in a very stable way. So if you want to compute high dimensional models, when you have very complex images, you'd better not try to build the model of the image themselves, but rather of the interactions, the exchanges between the high and the low frequency at each of the scales. Now, we applied that kind of thing to model weak lensing in cosmology. So what is the issue in weak lensing? In weak lensing, you have background objects, which are galaxies, that you are visualizing with your telescope. And because in between you have some very strong masses which are going to deform the trajectory of flight, these images are going to be deformed as if you had gone through a lensing. And if you can characterize the statistics of these weak lensing images, and there is going to be a new satellite called Euclid that is going to be sent just to measure these, then you can compute the distribution of masses in the universe. And with that kind of models, you can indeed build such models of these weak lensing images and then regenerate these weak examples of weak lensing images just by building models of conditional probabilities of wavelets given the low frequency. But these are too simple to go to turbulence. What are we doing right now? What we are essentially doing is taking an image. It's like a very simple deep network with a wavelet transform, which each time computes the different wavelet coefficient. And we're just looking at the interaction at one layer, at each layer like that. That works for a simple image such as these bright dots, but not for turbulence. Why is that? Because you don't capture the dependencies across scale. And if you come back to an image where you have geometry, such as this boat, you can see that at each scale, you see more or less a boat, even along different orientations. So these images are very strongly dependent. And the difficulty of building a model of images is specifically to be able to capture these dependencies across all directions, all scales. Now, why is that difficult? You could think of just computing a correlation. The correlation, let's say, of the wavelet coefficient at a given frequency with the wavelet coefficient at another scale, another orientation, different position. The problem is that the correlation is always going to be zero if you pick wavelets that have different scale or different orientation. Why? because these wavelets are supported over different frequency bands. So correlation is always zero. And the reason is that you have oscillations because of the phase, and these oscillations are going to cancel and produce a zero correlation. How can you avoid that? One simple way, and that was introduced by Simoncelli and Portilla, is essentially kill the phase. If you kill the phase and look at the correlation of the modulus, obviously you're going to get something which is non-zero, and it's going to give you information about the dependencies of what's happening at different scales. Now, here you get very large correlation matrices, which depends upon these translation parameters. So to nearly diagonalize these matrices, what you can do is do a second wavelet transform. So take these modulus of wavelet transform, retransform it with a new wavelet transform so that the correlation matrix is going to be reduced to very few coefficients. So that's what is leading to these scattering network, which are very plain vanilla models of neural network, and we'll see how far you can go. First, you do a wavelet transform. Then you do a second wavelet transform after applying a modulus. And then you normalize the value at each scale exactly like in the renormalization group. And then you compute the correlation at each layer. If you do that, I'm going to show that you can reproduce images which are very close to what was obtained by these deep nets. To do that, you need to regenerate. So that's what these deep nets were doing with a gradient descent. I just want to explain in information theory terms to what it corresponds to. What you have is a representation obtained with features, okay, which is here, the phi of x. You have one realization, one example of images, x0. So you have your features of x0. If you have an ergodic process and you've been averaging over a domain which is large enough, like empirical covariance, you know that for any image which is a realization of your stationary process, you should have nearly the same empirical moments. So what you are going to impose is that your model is going to be the set of all images which have nearly the same empirical models as the one you observed on the image. And that's going to define a set, and you're going to define a maximum entropy distribution, therefore, that is uniform over this set. Then what do you know? You know that your true distribution has to be inside, but the both may be very different. If you don't have enough information, you don't specify well enough the true probability distribution. So the game is how to find these moments that are going to be sufficient statistics to characterize the probability distribution. One way to test it numerically is to randomly find a point in your model space and look whether it looks like a true realization of the signal. And one way to do that is to use the same kind of strategy that we're using in these deep nets. You begin with Gaussian white noise, so somewhere on the sphere of your space, and you do a gradient descent in order to match the moments of the observed image, which should lead you to a point in that domain. If you do that with the moments of the scattering transform, and that's the work of Erwan Alice, Antoine Brochard, and Sifin Zhang, if you begin from an x0, which is turbulence, you get realizations which indeed looks like turbulence. This is an astrophysical turbulence of mixture of gas, of helium and hydrogen, and here you get the realization. This is a texture of bubble. This is a new texture of bubble, which is reproduced just from these moments. Cherries even, that you can reproduce with that kind of moments, which provides information across the different frequency band, angles, and here also colors. So that seems to work out. And in this case, it looks like you don't need to learn. Another example, cosmological data. This is the original one. These are the syntheses. And here you can show that numerically you reproduce the high order moments and you can estimate the cosmological parameters. Does that mean that you can do deep nets without learning? No. The reason why you can do it in these cases is because the fields are not so complicated. They are ergodic, they are stationary. You don't see faces or structures like that. So I want to move now to classification and show why you have a much more difficult challenge in these cases. I said, when you look at these deep nets, they seem to concentrate the data in different regions for different classes. What you want in this case to understand, again, is why it concentrates, it separates, the role of nonlinearities, and what do you need to learn about these filters. So what people usually use are rectifiers. One way to look at a rectifier, which is here, is to decompose it into an even part, and that looks like an absolute value with potentially a dead zone if you have a bias, and an odd part. And the odd part, this is a soft thresholding operator. This is something that is going to set your data to 0 when it's below a threshold and keep it modulo subtraction of the threshold when it's larger than the threshold. So in some sense, the ReLU is able to do both of them. One question is, which one is important? To kill the phase or to threshold for getting performance by a deep network? Now, what is a scattering network doing? The scattering network is imposing the filter and then killing the phase. It takes a modulus. So we repeat, and then you propagate everything to the last layer, where then you can do potentially a linear classification. So you can view these networks that I have presented previously as a kind of deep net with no connection across channels and no learning. What is the role of modulus in that context? Whenever you apply a filter, which is a wavelet, it has a real and an imaginary part. So if you take the modulus, which is shown here, it's also going to have a phase which is going to oscillate. If you translate your wavelets, it's going to change the phase of the wavelet. If you translate the signal and you make a convolution with the wavelet, it's like in the Fourier domain, it's going to introduce a phase. So when you take the modulus, essentially you kill the phase which is due to the local translation. Now think about it. If you have a phase which varies because of translation variability, your point may move on any location around this circle. And if you have two classes, you are going to have two kinds of circles like that that may be different because of the modulus. But if you take an average, any linear classifier, they won't be able to distinguish them because they have the same mean. If you take a modulus, you collapse the phase, you are going to simply separate the two classes, which are now linearly separable. So the modulus phase collapse allows you to separate things whenever you have variability due to translation, or it may be other group structures. Now you may say, okay, but you don't have any complex coefficient in these networks. First of all, this phase can be also exist also of a real number. It's just a change of sign. But also when you look at the networks such as AlexNet, you look at the first layers, the filters looks like wavelets. And in fact, you have filters which have nearly the same direction and frequency, but do have different phase, as if these networks were collecting information within different phase channels. So let me skip that and go to classification result. Let's first begin with a simple network which just does a scattering transform. So you apply a wavelet transform, apply a modulus, wavelet transform, a modulus, and at the end you average, and you just do a linear classification. If you do that on a simple problem such as discriminating digits, with a deep network where everything is learned or a scattering transform where nothing is learned, you get about the same result. The reason is that the source of variability when you want to recognize a digit is essentially local translation or global translation. And that's very well dealt with these modulus, which builds invariants. If you take a real image, that's CFAR, which is a database of small images of 32 by 32 pixels. You want here to recognize that it's a car, a boat, or let's say here a dog. If you do that with a scattering transform, the error is about 4 times bigger than what you get with a ResNet, 8%. If you go to ImageNet, where now you have 1,000 classes, much bigger images of about 256 square images and 1 million pixel images, to train, again, if you don't learn anything, the error is 4 times bigger than what you would get with a ResNet of, let's say, depth 80. So obviously, learning is absolutely needed here. But what is learned? And what is the role of the nonlinearity? So, as Michael said, I worked a lot on sparsity, and many of us worked a lot on sparsity. So one reaction is to think, well, sparsity must be the main reason, because essentially it allows to find isolated features and then classify on these isolated features. So it's this idea that basically you are building a model where you eliminate clutter and you find the sparse discriminative features. Why would a soft thresholding be a good idea? Because if you have classes and if you find a dictionary where these class means are sparse and well discriminated with different support, if you have some variability within your class, like modification, deformation, change of color, you can think of that as an addition of variability of noise. And if you do some kind of thresholding, which eliminates the small coefficient, hopefully you are going to recover the structure of the class itself. Okay, so I'm now going to compare what you get by collapsing the phase, which is the even part of the ReLU, with a thresholding, which is the odd part of the ReLU. And I'm going to do that, and that's the work of Florentin Gut and John Zarka, over a scattering network where you learn the interactions across channels. So the filters are all wavelets, spatial filters, but at each layer, you learn the interactions, as in physics, with a 1-1 convolutional filter that is going to be learned. It's this projector, which also reduces the number of channels. Then again, you compute a wavelet transform, and then again, a 1-1 convolution operator. That's the only thing we learn, which is here. Wavelet transform, 1-1 convolution operator, and each time I apply this nonlinearity, which may either be a thresholding or a modulus which kills the phase, and so on. Okay, so this is a visualization again of the network. All the filters are wavelets, but you have this 1-1 convolutions which relates the information across channels and that you learn, and you apply the nonlinearity. Okay, first thing, you apply a scattering transform. So no learning, the nonlinearity is a modulus. And what we saw is that you do much worse than the ResNet, which is a bit deeper, because the number of layers for a scattering transform is the log of the size of the image, so of the order of 6 here. But still, the difference is huge. Okay, let's now learn these operators and put a soft threshold. So I'm just sparsifying, and I'm learning the bias in order to adjust the threshold. If you do that, we did it on CFAR, you don't improve. In fact, it's even worse than the scattering transform, where you didn't learn anything, but where the nonlinearity was a phase collapse. Now, let's again try by learning these operators, but with having a nonlinearity, which is a modulus. And now you have a big jump and you reach the ResNet classification. So what it means? It means that, in fact, you don't need to learn the spatial filters. The spatial filters are just here to essentially separate the different frequency bands. What you need is to understand how these frequency bands interact in order to build up your probability distribution model. If you do learn them without learning the spatial filter, you get back the kind of results that you obtain with deep net classifier. However, it's very important that the nonlinearity kills the phase. And why is that so? Because the phase oscillates again because of transformation, such as these local deformations, or even transformation across color spaces or rotations or whatever groups. So killing the phase is a very important element which reduces the variability and which separates the different classes that are otherwise not linearly separated. Of course, the question that comes out next is, what are the properties of these type of 1-1 operators that are applied and magically leads us to standard deep net results? And that's a difficult problem. It's difficult because when you begin to look at these coefficients, the first layer coefficients, you can get properties, you can see that they give information about variability along rotations and so on. But when you go into deeper layers, it gets much more complicated. And the difficulty of the problem is that you are dealing with probabilistic models of objects which are very complicated, like cars, dogs, and so on. And that's where, in some sense, going back to problems which are more physical is easier, because they are physical models you can try to compare with. Okay, so let me stop by concluding. The first thing is that, I do very strongly believe, and that's shown clearly both by the numerical results and the type of algorithm that are developed, that the theory of deep network is not a theory of a functional analysis of an X that would belong to a block, let's say 0-1 dimension D, but it's a theory of high dimensional probability distribution, where you have to see where your data is concentrating. And this is at the core of statistical physics. That's why there is a very interesting exchange nowadays between statistical physics on one side and learning on the other side. As I said, this idea of concentration is absolutely key in information theory, but you also see it in these deep networks. Not only do they concentrate these probability distributions, but in a very smart way, they're able to separate these different probability distribution in different regions of the space, so that then a simple linear classifier does the job. So what it looks like is that on the way, the nonlinearity seems to partly or essentially do a phase collapse. In other words, it's not so much the sparsity phenomena which is important. It can play a role, but let's say that it's not sufficient. It's really the fact that you eliminate phases which corresponds to different type of variability that progressively allows to concentrate your probability distribution. Now, what is the goal of that kind of work? The goal at the end of the day is to be able to specify the classes of probability distribution that that kind of machines or algorithms are able to approximate. And that's important because you also want to understand what kind of distribution they cannot approximate and when there are going to be issues of robustness or strong errors. So that's the type of mathematics. There is obviously a very large community now which is beginning to work on these kind of problems, which are, let's say, essentially open. Thanks very much.